please take it away.
Hello, I'm Jeff. Well, I guess we have to wait for this thing. Yeah, Polkadot. I'm speaking about the protocol that's been used in Polkadot for sharding since 2021. Polkadot also has an interesting DAO problem, so I'll make people read his paper. Okay, so this paper is ePrint, the crypto ePrint 2024 961. So there's a lot of co-authors because we had a lot of people involved, including implementers. It was originally sort of me and Alistair and Rob Habermeyer who worked through the design of it, but it takes a lot of people to maintain something like what I'm going to show you. Okay, so all of Web2 requires sharding. So this meaning horizontal data partitioning. I mean, real services grow, and there's no way you can do it with one machine. Blockchains simulate a database through auditing. This is fundamentally what they do. The machines audit the updates. But that they're basically simulating a single threaded database. It's kind of shitty. So are they only for these toy services that we're using them for now, or can we actually make them scale up to run real things? So what that means is, one of the things that means is we have to make the auditing more efficient. Okay, so block auditing protocols just means how the blockchain checks blocks or checks the blocks of other chains or whatever, things like this. So the questions you have to ask, one question is it provably secure and under what assumptions? And how much does it cost in computation, bandwidth, opportunity costs on the nodes, and energy? So at least the first two of these, we can actually, as a kind of a course reference, we can just say costs in terms of number of machines is actually a reasonable metric. Of course, it's more nuanced than that. There's other protocols, other questions I'm not going to be talking about here, like censorship resistance, liveness, and the machine storage. Okay, so a simple example of a block auditing protocol is a bridge. So you have a bunch of blockchains and they're all bridged together. The basic disadvantage of this is as you add more blockchains bridged together, then you're still assuming 2/3 honest on each of them, so the protocol security will drop if you're interacting with a bunch of them. So eventually we should see the bridge ecosystems have very interesting attacks that involve a human element and other things. Another one is these optimistic rollups. Generally, these things are not provably secure, or if somebody does manage to do a security proof, it will probably involve a lot of wild assumptions, like not explaining why validations are happening. Because they have this problem, they generally have some kind of inter-shard latency which is of like a week, or at least the current big ones do. So that's also kind of shitty. You don't want your sharded database to need a week of latency between shards. So a more serious thing is these ZK rollups. So we have a succinct-ish cryptographic proof for each block. These are great because they have very weak assumptions. Exactly what depends on what you're doing. Like Mina would be, if it's verifying the ancestry like Mina, then that changes your Byzantine assumption, improves your Byzantine assumptions even. This is cool because they're recursive, very composable, very good, but they're very expensive. So just quoting Justin Thaler, that generally they're 1 million to 100 million times the cost of a single verifier in terms of CPU time. So we're interested in total CPU time, like the actual costs, not just the on-chain CPU time. So those numbers are not the end of the story. If you're Ethereum and you're paying 500,000 or 1 million nodes, that's great. You save 1 million times the bandwidth. But anyway, some of these things are ending up with inter-shard latency of like an hour, and this will worsen MEV. That's still a problem, and there will be very high opportunity costs because of the need to be able to do all this computation. And also, a lot of the assertions that these things will improve are like using specialized hardware. Of course, anybody can use specialized hardware. It's not unique to them. There's nothing special there. So the real question is about the algorithms. So what we're going to be talking about is transparent verification. And if ZK things can improve that, great. But okay, so true sharding, this is not what we do. Eventually, everybody will be doing this. There's a paper on it by Brian Ford's group at EPFL. The way it works is you take a very large set of validators, you assume some higher honesty threshold, like 80% honest, and then you put like 1,000 validators on each shard, on each chain. And then you use some kind of concentration inequality like Hofding or Chebyshev to argue that you have 2/3 honest on each of those chains with very high probability. Concentration inequalities prove that things group towards the mean a bit. Okay. So what's cool about these things is that they can do everything. Like the entire distributed system can be put into this kind of sharding. So you can be running all kinds of off-chain protocols, and so they're kind of magic. They're much better than ZK rollups at the distributed system side. Intershard latency can be seconds or minutes, but it happens after sort of finality from the different shards. So your bridges are fast within this large set of validators. The bridges are fast and trustworthy. They don't really have any other disadvantages other than the sorry, I missed the first line here. So of course the advantage is that it's 1,000 times cheaper than a ZK rollup into CPU, but it's 1,000 times the bandwidth cost of a single verifier. So like 50 times the bandwidth cost of a ZK rollup. A decentralized one. So we don't need recursion here because of the way the assumptions are working. The other kind of pseudo disadvantage is people think they can do it and they fuck it up. Even the professor coins screw this up. Like Definity has 15 to 40 nodes on a shard, and I'm not sure they assign them randomly either. I have no idea. Okay, so I'm going to be talking about the sharding in Polkadot, which eventually we will need this true sharding that I just explained on the previous slide as well. But what we're talking about is sort of sharding for smaller sets of nodes. So I'm going to go through 4 tools that we need. The first is soundness slashing. Slashing is generally pretty evil. Professor coins don't do it. It's also pretty necessary for a lot of Byzantine stuff. So it's what it is. Soundness slashing is not as nasty theoretically as all of the slashing you need from a Byzantine perspective. You simply need, for soundness slashing, you absolutely need a provable violation, and you can't have any sort of gray area, and then you need to know sort of you need to know sort of what's the value you're protecting, and then you can argue your soundness error. So a soundness error of less than 20,000 to the -1 is perfectly fine. So 1 over 20,000 is perfectly fine if you're trying to protect. If you have sort of 5% of the value, of the value of the network in stake. Okay, that's in total stake. Okay. Right. So another tool we need, which people probably know about, is we need stateless blocks. This means, so in Polkadot, the blocks are coming from these side chains. We call them parachains. And the parachain has to attach state proofs. So we're doing transparent validation everywhere, so that just means they're attaching Merkle proofs to their blocks, which blows up the size of the block quite a bit. You could do other things. KZG is too slow. Maybe there's some other flavors of KZG which are better. The two last talks on the first day are kind of interesting. Latticefold, maybe if you use some lattice-based hash functions, whatever. But ultimately, we're doing this computation versus bandwidth trade-off, and right now we're pushing on the bandwidth side. Maybe we have to change that eventually, but anyway, all right. So another tool is availability commitments via erasure coding. So the general idea here is that the block body becomes a code word in erasure code, and then it gets chopped up into little chunks. And then you have a Merkle tree that commits to those chunks. And the questions you should ask of an availability protocol are the chunks retrievable, and how do you know that the encoding is correct? So there's the popular one is this 2-dimensional Reed-Solomon. It has a really shitty undecodable ratio of like a quarter. That means a quarter of attackers can hide the thing. So they have to do a lot of sampling, use a lot of bandwidth to deal with that. And then the reason people like it is because they can do these fraud proofs from only a small chunk of the block. But this doesn't matter very much because the validity is not a property of the whole block. Validity is a property of the whole block, not of the transactions. It's useless to see a small part of the block in general. We only care about what a full block does. So not interested in two-dimensional Reed-Solomon. One-dimensional Reed-Solomon, with 1/3 threshold gives us the attacker must hide 2/3 of the block of the shards to do anything. So it combined with 2/3 honesty assumption, we're great. 2/3 vote yes, 2/3 honesty assumption, we have 1/3 left over, we can reconstruct. So we're putting one chunk per node, which is also different from how the 2D Reed-Solomons work. So the total bandwidth of doing this is about 3 downloads of the full block. This is very efficient. And again, as I said, we're doing all or nothing reconstruction. So whenever we finally check, essentially, as the previous thing was taking a small block and making it larger or as the stateless block is taking a small block and making it larger to make it stateless. Now we're taking the stateless block and we're making it 3 times bigger in a sense and so that it can be distributed in chunks. And so when you check the block, you will have to check these chunks. All right. Now, there's a number of other reasons. I didn't go into this about the Reed-Solomon, but when you want things like batch verification and whatever, this stuff is only efficient when you can check the full block all at once. All right. All right, so let's talk about actually the protocol that we use. So it's kind of you can think of it as a kind of a cut and choose protocol. But under Byzantine assumptions. So we're assuming 2/3 honest, plus we'll be assuming synchrony in one place that I'll get to, and also this soundness slashing. So the parachain makes these stateless blocks, and they passes it to this relay chain, which you can think of as like the beacon chain on Ethereum. There's a few interactions on the relay chain that have to do with availability primarily, but actually a huge amount of the complexity of the protocol is going from the parachain to the relay chain. This turns out to be extremely complicated, and that's going to impact everybody who's doing lots of things. But anyway, because you don't want to mempool, it has to be more efficient than that. Okay, so what happens on the relay chain is some validator declares responsibility, and they do this erasure coding, and they ship out the chunks to everybody else once the relay chain acknowledges that they've declared responsibility for this block. That shipping out the chunks, all the other validators are kind of voting on these bit fields of whose chunks they have received. This gives an efficient proof that the block will be checkable in the future because we now have all of these pieces. So now, at this point, we have not proved the thing yet, proved these parachain blocks are correct, these parablocks are correct, but somebody's on the hook for them, and we know they can be checked. So we're just going to go ahead and optimistically send all the messages. So this gives us inter-shard latency of tens of seconds. All right. What happens now? The nasty part. So what's going to happen is there's this kind of approval gadget, which I'll explain in a second, and the validators are self-assigning using verifiable random functions on what they're going to check of the incoming parachain blocks. And basically, we just delay finality until everything is approved. So the entire validation process, the actual validation process, is basically a delay on finality, or causes a delay on finality. If anybody disputes in this process, we escalate and everybody checks, and we just make that economically viable. And if any of the disputes pass, if any of the disputes conclude that the block was invalid, then we just kill the backer, the guy who originally is on the hook for it. So that's basically a $2 million fine. Okay, so the advantages of this protocol, like I said, inter-shard latency of sort of tens of seconds. We only need about 30 to 35 checks. Actually, it's probably a little high. It's probably about 26 to 30, low 30s. So this makes it about 29 times cheaper than OmniLed, than the true sharding. And we probably will get this down further with some protocol changes. So it's going to be really hard to beat this in terms of total CPU time. And we basically will prove security by exhausting the stake under an attack. So another advantage, this whole protocol was designed to pipeline and batch very well. Disadvantage, you need all that pipelining and batching to make it efficient. It's of course complicated, going to be complicated, and this soundness slashing is nasty. And as I said, there's going to be a synchrony assumption in here. And the other thing is this thing, I've been talking about scalability. Alone, this thing is not really scalable because gossip isn't scalable and we need gossip. So in the end, what this protocol does is it scales us up to a sort of 1,000 validators while having only about 30 check each thing. And then you have to use true sharding and assume 80% honest beyond that. But we haven't done that yet. Okay. So okay, so first, what does one of these auditing tasks actually look like? So the first thing that happens is there's a local VRF that tells each validator, each node, who they're supposed to be, which things they're supposed to be checking. I'll talk about those on the next slide. And they have to announce these. This is the place where we're assuming synchrony because we need people to know who's supposed to check what. But then after they do this, they reconstruct, and so in the synchrony, sorry, one more comment about the synchrony assumption. We're sort of willing to do anything here to enforce synchrony, like use specific UDP packets or various other things. But we can get this into sort of a single packet. Okay, so the rest of the auditing task is you reconstruct from availability, you re-encode to check the erasure routes. This is checking the erasure coding, the original erasure coding. And then you actually check the block itself and announce the results. So that's what an auditing task looks like. And now how do we decide what happens? So who's doing what? So there's 2 VRF conditions that decide what people are going to be auditing. The first one, we call it tranche 0. It sort of samples widely across all of the incoming parachain blocks. And the important thing here is that the number of samples each validator uses is supposed to be this, the number of checks we want, the base number of checks we want on each one of these things, times the number of validators is supposed to be the base number of checks times the number of cores or the number of tasks that we're trying to simulate or that we're trying to run. So after this happens, there are other tranches that can check, and what happens is if the validators just sort of sample a kind of a delay, we call it this tranche number, and everybody is assigned to check everything at some delay, and what will happen is they'll only be triggered to check by somebody who announced that they're going to check something failing to do so. Basically, if somebody doesn't check for 12, if we don't get any response from a validator for 12 seconds, then whatever work they were doing will get checked by 2.25 other guys in expectation. So, okay, now that 2.25 means that if you have a 1/3 adversary, then you're checking by, in expectation, 1.5 honest guys. And the point is, eventually, every validator either approves disputes or becomes one of these no-shows. All right, so why 2.25? We wouldn't want to have 1.5 or less because then the number of honest checkers would only be 1, and in principle, the adversary can exhaust it. We wouldn't really want to have more than 3 either, because then it would take a relatively small number of malicious nodes to cause, or just nodes going offline to cause some disputes. And you can look. This is some computations from the paper on sort of final committee sizes, based on the size of this F delta or yeah. All right. So that was one important thing, is the size of these non-zero these tranches after 0. How big do they have to be? The other question is, how big does this first tranche of checkers have to be? And the computation for the paper looks like this. Just doing some probability theory to come up with this. But it depends. So gamma's the proportion of dishonest nodes. so it depends on this soundness error, and also on the proportion of dishonest nodes, and then on the and it depends as well on this how many we're signing per later tranche. Originally we just worked out this number 30 here using simulations. I guess the number is really 26, but because the simulation code wasn't that great in some ways. But right. So here's sort of a graph of the trade-off between the size of the initial committee and how big of a size of the later tranches to still be able to prove security. So we're currently up in the epsilon Polkadot's working with at the moment is something like 100,000, not just the 20,000. So we're well into the safe range. All right, so some other things I want to, so what is actually something about the real performance? So we're running something like 6-second block times on the relay chain. Parachains can run faster via what's called elastic scaling. So this means that the parachain can make blocks in multiple sort of core slots of the relay chain, and the relay chain will just check that they chain together. This means, at the moment we don't let them go that fast, but they can go pretty fast if they want to. The parachain blocks are 5 megabytes and have about 2 seconds of single-threaded WASM. There's a RISC-V bytecode we're working on called PolkaVM that will be better than WASM for this. As I said before, we've been running this since 2021, slowly improving the bottlenecks. Currently, this Kusama network has about 100 parachain slots on 1,000 validators, but we'll definitely get it to 200 next year. So that means we'll be running about 1 blockchain for every 5 validators, and we'll probably get it to 1 every 3. How much more than that, I don't know. One of the major things here, one of the major constraints is so we can force upgrades of software. That's the only way we're able to build the system, is being able to actually do upgrades. But we can't really force our upgrades of hardware yet, so a lot of the nodes are too weak. The recommended node size was only 4 CPU cores. That needs to be improved, and we have a lot of assets who run like 2 cores. So we're getting a lot of performance out of some relatively shitty machines. That will be improved. We have a protocol that will tie the rewards more closely to what people are actually doing. It, again, also runs off-chain. So some observations. This protocol gains dramatically from being run off-chain. If you wanted to try and make an SZK, roll up off of this, it would be nasty. The small per block committees that we get may be useless without this soundness slashing. These no-shows that I was talking about, they happen. We get about half a no-show to a no-show per block, depending on what kind of upgrades we've done recently. That just happens. It's fine. We've only had a few escalations, but generally they were our fault, so you need a DAO to be able to reimburse people when things go wrong. So the system depends on being able to have a DAO. An anti-upgrade ideology would have made all of this impossible. And there's a bunch of complexity that I've hidden under the rug in this talk. As I mentioned, that the flow between, just between chains is actually really nasty to do correctly. Generally this protocol has required a lot of benchmarking and figuring out what needed to be worked on to get it where it is. I think that's all I want to talk about, so I'll just take questions.
Okay, thanks for the great talk. Are there any questions from the audience? Okay, while people are thinking, I actually have a question. Could you go back to the equations line before the graph?
This?
Yeah, is this W0 the Lambert W function?
Yeah.
Okay.
Yeah, because when you're doing the computation, it's the correct branch of this thing, because the other branch would give you the same thing, the input back out, and you don't. Well, yeah. Anyway. This is in the paper, the arguments for it.
Yeah, I was actually skimming through the paper and realized you guys have a parallel contribution on strengthening Cantelli's
Sorry,
lemma.
can you
A
repeat?
parallel contribution on strengthening Cantelli's lemma. I think.
Parallel.
Like you were strengthening an equality in probability theory, Cantelli's lemma.
Okay, yeah. I mean,
Could you-
so our Alistair Stewart is very much a real like his PhD was in robust statistics and did very interesting work there before coming here.
Yeah.
Yeah. So the probabilities don't scare us.
Great. Yes, there's a question.
I was wondering if you had any way to address essentially the lazy validators problem, the notion
So that's essentially what I was talking about. Here that we sort of created our own lazy validators problem because when the first system was initially designed, so Gavin originally designed what was basically an optimistic rollup. This was Alistair Stewart and Rob Habermeyer and me and then all these other people that on the Parachain team and the research team that changed it to be this way. So originally when they were first making specs for Substrate, they were just like, oh, we need fast single-threaded performance, but we don't care about cores. So we put down recommended 4 cores, and we have a problem that people run only 2. So even if they're not lazy, like intentionally lazy like you're thinking, we already have a lazy problem that they may just fail to check and cause no-shows and other people will work. So the answer, I didn't talk about it at all in this talk, is this. So part of it will be this reward system. And we're also very careful about we're very careful about this. So I didn't talk about this either, but we have slashing that happens. So if you cause a dispute or an escalation, because remember, this system will escalate on its own, even if there's no dispute. Like if people just aren't checking. If you cause that, you will eventually get slashed.
So presumably a malicious lazy validator could say that they checked the block, thus they wouldn't
Sure.
qualify as a no-show.
So there's nothing we can really do about. So an important thing to remember there is that there aren't that many other people checking it. Yes. So this is definitely a risk. They're risking a great deal of money. It's the only real answer there. Another part of our system. It makes that more risky, which is this NBUS thing, which what it does is so in the system all validators are effectively equally staked because we solve this voting theory problem to try and assign stakers to validators, but I would say the real problem there is less the specific lazy validator problem that you're thinking is that the nominators, the people whose stake is being applied to the validators, aren't actually checking. So in the same sense as Tor has to have meetups where they like teach validator, Tor node operators things like how to talk to cops and whatever, we really need to have meetups between nominators and validators to try and maximize the chances that the nominators actually know the people they're nominating. And the whole view of, in my personal opinion, is the whole view of thinking of staking as this financial thing is a disaster from the security perspective. Yes, we do have that problem. The only real answer is that you lose a lot of money.
Thanks.
And we have to keep the rewards high to make sure that,
Right, let's thank the speaker again. This concludes the session. There must be lunch outside.